Close your eyes for a moment. Picture yourself standing in the middle of a vast desert under a star-filled sky. There's no noise, only the whisper of the wind and the distant hum of stillness. Above you stretches the night, endless, mysterious, quiet. You look up, and all you see are stars, scattered like ancient lanterns on a black canvas, each one a sun, perhaps with worlds of its own, spinning through the great ocean of space. In a moment like this, it's easy to believe the universe is calm, drifting, eternal, that what we see is what we get, a quiet cosmos, aging gracefully as time marches on. But what if, behind this veil of silence, something is stirring, something powerful, yet utterly invisible, something that doesn't glow, doesn't shine, and doesn't seem to interact with anything in any conventional way. And yet it's everywhere, inescapable, subtle, and strangely dominant. This is dark energy, an unseen force, a ghost written into the equations of the universe, a silent pressure, not one we feel on our skin or hear in the air, but one that acts on galaxies, bending the fate of everything that exists. It doesn't crash or explode, it simply pulls everything apart. And here's the most astonishing part. Dark energy may account for nearly 70% of everything in the universe. 70%. That means all the galaxies, all the stars, all the dust, gas, and particles, even the mysterious dark matter that clumps invisibly between galaxies, make up just a tiny fraction of the cosmos. The rest, the vast majority, is this strange, repelling, invisible presence. Let's pause for a moment and let that sink in. You are made of atoms. Everything you know, your thoughts, your memories, the people you love, the planet you live on, the stars you see at night, is made of normal matter. But all of that combined is just a sliver of reality. Dark energy is the ocean. We are the foam. This idea wasn't always part of science. In fact, for most of human history, we didn't even know the universe was expanding. For a long time, we assumed the cosmos was static, eternal, unchanging, infinite. That view began to shift in the early 20th century, when astronomer Edwin Hubble observed that distant galaxies appeared to be moving away from us, and the farther away they were, the faster they seemed to go. This was the first clue that the universe was expanding. Not just galaxies moving through space, but space itself stretching, carrying galaxies with it like raisins in a rising loaf of bread. Naturally, scientists assumed that this expansion must be slowing down over time. After all, gravity pulls things together. Even if the universe started with a powerful bang, a big bang, wouldn't gravity eventually apply the brakes? That's what everyone expected. Until the 1990s. That's when something truly strange happened. Two independent teams of astronomers, using exploding stars called Type Ia supernovae as cosmic measuring sticks, found that not only was the universe expanding, but the expansion was actually speeding up. Against all logic, the universe wasn't slowing down. It was racing ahead faster and faster. It was as if some invisible hand were pushing galaxies away from one another with increasing force, like a car accelerating downhill, except no one knew who was pressing the gas. That invisible hand was soon given a name, dark energy. But what is it? That's the question that still haunts cosmologists to this day. We know what dark energy does. It makes the universe expand faster, but we don't know what it is. And so we call it dark. Not because it's black or evil or hidden in shadow, but because it is, quite literally, unknown. It's not dark matter. Dark matter is another mystery entirely. Something that has mass and pulls things together with gravity. Dark energy is the opposite. It pushes things apart. It acts like a kind of anti-gravity on cosmic scales. So what could it be? Some theories suggest that dark energy is the result of the cosmological constant, an idea first proposed by Albert Einstein over a century ago. He introduced it to keep the universe from collapsing under its own gravity. but later discarded it when Hubble's expansion was discovered. Ironically, his biggest blunder may turn out to be one of the most prophetic predictions in modern science. Other theories are more exotic, proposing new fields of energy, or unknown particles, or effects from extra dimensions. But no matter how we frame it, the basic truth remains. Space itself is not empty. It's not just a background stage for matter and light. It has energy, and that energy may be driving the entire universe toward a future we barely understand. Take another breath. Let the idea settle gently in your thoughts. Now imagine this. Each second, the space between galaxies grows wider. But not because anything is moving in the traditional sense, not because galaxies are flying through space, but because space itself is stretching. And the farther apart two galaxies are, the faster that space stretches between them. This is why the universe has no center. It's not expanding from a point, it's expanding everywhere, all at once, like the surface of a balloon being inflated. The dots on the balloon, the galaxies, get farther apart as the balloon grows. Dark energy, it seems, is the thing inflating the balloon. But we don't know what's in the pump. Now consider the implications. If dark energy remains constant, never changing in strength, the universe will continue to expand faster and faster until galaxies vanish from view, their light stretched so thin it fades into darkness. Stars will die, planets will freeze. The universe will become a cold, empty void, a future known as the Big Freeze. But if dark energy gets stronger over time, it could eventually rip galaxies apart. Then star systems, then even atoms, until nothing holds together. This catastrophic possibility is called the Big Rip. And yet, if dark energy weakens or reverses, gravity might eventually slow down expansion and pull everything back into a final collapse. The Big Crunch. We are caught in a cosmic tug-of-war between forces we don't understand, drifting inside a mystery that defines our very existence. The silence of the night sky is not so silent after all. It is filled with motion, quiet, unstoppable, ancient. The galaxies are not just drifting. They are being pushed, compelled by something woven into the very structure of reality. Take a moment now to reflect on this silent force. Let your mind drift with the galaxies. Let the mystery be a comfort. You are part of something vast and unknowable, not lost in the universe, but moving with it, gently and endlessly outward. And as we drift deeper into this mystery, one question beckons us forward. When did dark energy begin its silent work? And how did we first detect its presence? Let us continue our journey back to the night sky of 1998 and the moment the universe revealed its hidden acceleration. There are moments in human history when everything changes, not with a roar, but with a whisper, not with trumpets or grand declarations, but with data, quiet numbers, distant light, a flicker in a telescope lens, a strange pattern that doesn't belong. The year was 1998. Most of the world was focused on earthly things, politics, sports, the internet, daily life. But in observatories scattered across the globe, a handful of astronomers were staring at something much older, much larger, and much more mysterious than any headlines. They were watching the past. They were watching stars die, and what they found would shake the very foundations of cosmology. At the heart of this quiet revolution was a simple question. How fast is the universe slowing down? Not if it was slowing down, because everyone assumed it must be, but how much? You see, after the discovery that the universe was expanding, the natural follow-up was, will it keep expanding forever? Or will gravity eventually win and pull it all back together? This was considered one of the great questions in cosmology, and it seemed like one that could be answered with enough precise measurements. And so, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the deceleration of the universe. Their tools? Type Ia supernova, a very specific kind of stellar explosion. These aren't just any supernovae. Type Ia supernovae occur when a white dwarf, the dense core left behind after a star like our Sun dies, steals matter from a companion star until it reaches a critical mass and ignites in a thermonuclear explosion. Because this critical mass is always about the same, the resulting explosion is also roughly the same brightness, no matter where it happens. That makes these cosmic blasts incredibly useful to astronomers. They are called standard candles, objects of known luminosity. If you know how bright something truly is and you observe how dim it appears, you can calculate how far away it must be. It's like seeing a 100-watt bulb in the distance. If it looks dim, you know it must be far away. If it looks bright, it must be closer. Simple in principle, complex in practice. With this method, astronomers could measure the distances to far-off galaxies with surprising accuracy. They could then compare these distances to the galaxy's redshifts, a stretching of light that reveals how fast those galaxies are moving away from us. The plan was straightforward: measure the distances and speeds of these exploding stars, then use that information to chart the history of cosmic expansion. They expected to find that the farther away a supernova was, that is, the farther back in time it exploded, the slower the universe was expanding at that moment. Because gravity, they thought, would have been slowing everything down over time. But that's not what they found, not even close. When the data began to come in, it was odd. The supernovae appeared too dim. They weren't just far, they were farther than they should have been, based on the expected deceleration. The only plausible explanation. The universe hadn't been slowing down, it had been speeding up. At first, both teams were hesitant. The implications were staggering. If the universe was accelerating, then something was causing it. Something new, something unknown. And science, especially cosmology, doesn't embrace change easily. So, the teams double-checked, triple-checked. They verified their instruments, recalibrated their models, reviewed every detail with caution and care, and the results stayed the same. The universe was not coasting to a halt. It was racing ahead, faster and faster, driven by a mysterious force that defied gravity itself. It was one of the most shocking discoveries in the history of astronomy. It turned the question of how fast is the universe slowing down into something far more profound. Why is the universe speeding up? And that's when a name began to circulate, a placeholder, a concept wrapped in mystery, dark energy. It wasn't energy as we know it. It wasn't something we could see, touch, or interact with. But it was doing something big. It was making the universe grow. Let's pause here. Imagine the emotional weight of that moment, not just the scientific implications, but the sheer wonder of it. For decades, humanity had imagined a tug-of-war between gravity and expansion. It was a cosmic balance, a universal struggle that would define our destiny. But now, we weren't even part of the equation. The universe was slipping away from itself, and no one knew why. And yet, the more we looked, the more convincing the evidence became. The supernova data held firm. Other observations began to confirm it. Measurements of the cosmic microwave background, the distribution of galaxies, and later, surveys of gravitational lensing all pointed to the same conclusion. Something was driving acceleration. And it wasn't matter. It wasn't dark matter. It was something else. That's when Einstein's old idea re-emerged like a ghost from the past. You see, back in 1917, before the universe was known to be expanding, Einstein had added a term to his equations to prevent his model of the universe from collapsing under its own gravity. He called it the cosmological constant, a kind of repulsive force baked into the fabric of space itself. But when Hubble discovered cosmic expansion in 1929, Einstein abandoned the idea, reportedly calling it his greatest blunder. Now, decades later, the idea of a cosmological constant was back, only now it wasn't a mistake. It might be the key to understanding this new invisible energy. But is it really that simple? That's the puzzle that continues to haunt cosmologists. If dark energy is just a cosmological constant, just a fixed energy density of space, then it behaves very predictably. It remains constant in time, and it drives an eternal acceleration. But what if it's not constant? What if dark energy evolves? That would mean we are not just facing a quiet, steady expansion, but possibly a dynamic, shifting future with surprises yet to come. This distinction is more than academic. It touches the very structure of space, time, and existence. Is the universe a peaceful river flowing outward forever? Or is it a wild current, growing stronger, changing direction, capable of collapse or catastrophe? And then there's the most haunting question of all. Why now? Why are we alive at this precise moment when dark energy has just begun to dominate the universe? This question, known as the cosmic coincidence problem, is perhaps the most unsettling aspect of all. The energy density of matter decreases as the universe expands. The energy density of dark energy, if it's a cosmological constant, does not. Billions of years ago, matter ruled the cosmos. Billions of years from now, dark energy will reign alone. But today, right now, they are roughly equal in strength. Why? Is it chance? A fluke of timing? Or does our very existence depend on this moment? These are not easy questions, but they are the questions born in that quiet revolution of 1998, when two teams, independently, opened a new chapter in our understanding of the cosmos. They didn't set out to find dark energy. They didn't even believe it existed. But through meticulous measurement, humility before the data, and a willingness to confront the unexpected, they unveiled a deeper layer of reality. And yet, for all this discovery, dark energy remains a mystery. It has no identity, no known particle, no lab detection, no equations that explain its origin. We have only its signature, an accelerating universe. It is as if the universe whispered to us, not with words, but with light from distant stars, that the story is far stranger than we imagined. That what we thought was a silent drift through time is, in fact, a cosmic race, propelled by a force we cannot see or touch. The discovery of dark energy didn't solve the mysteries of the cosmos. It deepened them. It pulled back a curtain and revealed not clarity, but shadow, not answers, but echoes. And so we drift, expanding, accelerating, surrounded by a force that fills every void, stretches every distance, and leaves behind only questions. Let your thoughts rest here. Let them stretch, slowly, like the space between galaxies. Let them wander, like photons from a distant supernova, arriving not in years, but in centuries. This is the pace of the universe, not rushed, not loud, but always in motion. And as you relax into this gentle rhythm of cosmic thought, let us move to the next chapter of this mystery, because the question remains, what is dark energy? Is it truly a constant presence, like Einstein once imagined? Or is it something stranger, something alive, changing, shifting beneath the surface of space itself? In the next segment, we will dive into the theories. We will explore the vacuum of space, not as emptiness, but as something vibrant, flickering with potential. We will consider quintessence, the possibility of evolving energy fields, and even glimpses into the multiverse. The discovery of 1998 was not the end of the story. It was the beginning. Take a moment to settle in. Let your thoughts drift quietly, like dust floating in a sunbeam. Now, imagine space, not as a place filled with stars or planets, but as something deeper. Imagine space itself, not the things within it, but the fabric of it. What do you picture? Most of us imagine space as empty, a great void, a vacuum, cold, black, and silent. But that image, comforting in its simplicity, is wrong. Quantum physics tells us a different story. It tells us that even the deepest vacuum, even the most isolated corner of the cosmos, is not truly empty. At the smallest scales, far smaller than atoms, space is a churning ocean of energy. Virtual particles blink in and out of existence. Fields ripple without cause. This restless dance is known as quantum fluctuation. And so we arrive at a startling idea. Perhaps dark energy, the mysterious force accelerating the expansion of the universe, isn't coming from somewhere outside space. Maybe it's coming from space itself. This idea is known as vacuum energy. It suggests that what we think of as nothing is actually full of invisible energy woven into the very structure of the cosmos. In this view, dark energy is not an alien substance, not a new particle or force, but rather an intrinsic feature of space. As the universe expands, more space comes into being, and with it, more vacuum energy, continuing the expansion in a self-reinforcing loop. It's an elegant idea. Space contains energy. Energy affects gravity, and gravity, or rather anti-gravity, explains acceleration. But like many elegant ideas in physics, this one comes with a flaw, a spectacular one. When physicists try to calculate how much vacuum energy space should contain, based on quantum field theory, they get a number so large it defies imagination. Not just off by a little, not off by a factor of 10 or 1,000 or even 1,000,000. They're off by a factor of 10 120. That's a 1 followed by 120 zeros, the largest known discrepancy between theory and observation in the history of science. Some have called it the worst prediction ever made in physics. To put that in perspective, if you calculated the height of a skyscraper and were off by more than the size of the visible universe, you'd still be doing better than this. This mismatch haunts cosmologists. Either the theory is wrong, or the vacuum energy is somehow being cancelled out or balanced or tuned by something we don't yet understand. And so the question deepens. If vacuum energy isn't the whole story, then what else could dark energy be? One compelling alternative is something called quintessence. The name itself is poetic, a reference to the ancient belief in a fifth element, beyond earth, air, fire, and water. The pure essence that filled the heavens. In modern physics, quintessence is a hypothesized field, like the electromagnetic field, that fills the universe. But unlike the cosmological constant, quintessence isn't fixed. It evolves over time. You can think of it like a slowly changing wind that fills all of space. At times, it may blow harder. At other times, it may fade. The strength of this field could rise or fall, pushing on the fabric of space with varying pressure. This is one of the features that distinguishes quintessence from the more traditional cosmological constant model. While the cosmological constant assumes that dark energy is a fixed value, always the same, everywhere, forever, quintessence suggests that the universe's acceleration might change. That's a profound shift in perspective. If quintessence is real, then dark energy might not always dominate the cosmos. It could strengthen, it could weaken, it could vanish, or it could grow so strong that it tears the universe apart. Quintessence opens the door to a dynamic future, a universe whose fate is not sealed, but in flux, a universe where time may hold surprises yet to come. And yet, even this may not be the end of the story. There is another idea, one stranger still, one that forces us to question not only the nature of dark energy, but the nature of reality itself. It is the idea of the multiverse. In this view, our universe, vast as it may seem, is just one bubble in a sea of bubbles. Each universe, or pocket universe, exists with its own laws, its own constants, its own version of reality. In one, gravity might be stronger. In another, there may be no atoms at all. In ours, the value of dark energy is small, just enough to allow galaxies to form, stars to shine, and life to evolve. But it didn't have to be that way. If dark energy were just a little stronger, it would have stretched space so fast that galaxies never formed. Stars would never have ignited. Planets would never have coalesced. Life, as we know it, would have been impossible. If it were slightly weaker, perhaps everything would have collapsed too soon. So why this value? Why now? the multiverse offers an unsettling answer. There is no why. We just happen to live in the version of reality where things turned out this way. The laws of physics are not fixed by some divine necessity or elegant equation. They are random. It's a humbling idea. It suggests that the universe we know is a statistical fluke, one configuration out of countless possibilities. And this brings us to a strange kind of logic. In a multiverse filled with billions of universes, we can only find ourselves in the kind of universe that allows observers to exist. That is, if dark energy were different, we wouldn't be here to wonder about it. This line of thinking is known as the anthropic principle, a kind of cosmic selection bias. We observe this value of dark energy not because it's special or inevitable, but because it's the only value that allows observers like us to exist. It's a frustrating answer for many scientists. It feels more like philosophy than physics. It offers no equations, no predictions, no tests. And yet, it may be true. All three ideas, vacuum energy, quintessence, and the multiverse, reveal something important. Dark energy is not just a scientific mystery. It is a philosophical challenge, a riddle that touches the deepest questions of existence. What is space? Why does it behave the way it does? Is the universe tuned for life? Or are we just lucky? And if space itself is alive with energy, what does that mean for the future? If vacuum energy is correct, we must explain the greatest mismatch in theory and measurement ever recorded. If quintessence is real, we face a future of unpredictable change. And if the multiverse exists, we may never know why our universe has the properties it does, only that it does, and that we are here to see it. Perhaps most haunting of all is this. If dark energy is a property of the vacuum, if the very emptiness of space drives acceleration, then we live in a universe that is not stable, not still, not resting. We live in a universe that is always becoming, always unfolding, a universe that expands not because of some external force, but because of something intrinsic, something built into the structure of existence. This thought is both beautiful and terrifying. It means that space is not a stage upon which the universe plays. It is the play, the actor, the action, the cause. And we are part of that unfolding. Brief moments in an expanding sea of possibility. So as you rest, let your mind float across these ideas. Let them rise and fall like waves on a quiet ocean. Vacuum energy, quintessence, the multiverse. None are proven. None are final. But all are attempts to explain something that doesn't make sense, yet clearly exists. These theories are not answers. They are poems written in equations, hopes whispered into telescopes, invitations to imagine more. And now, with this groundwork laid, we can take the next step in our journey. Because while we've explored what dark energy might be, we've yet to explore what it might do. So let us ask, where is all this heading? If the universe is expanding faster and faster, what does that mean for the galaxies, the stars, the atoms, and the people that float within it? In the next segment, we will drift into the future, to the possible destinies of the cosmos. Will it freeze? Will it rip apart? Will it collapse into fire? The universe has a fate. Let's explore what it might be. Look up at the stars tonight. Take a breath. Let your eyes rest on their quiet flickering, so ancient and serene. These lights, scattered across the night like the final embers of a campfire, feel eternal. But they are not. Each one is burning fuel. Each one is a story with a beginning and inevitably an end. Just like stars, the universe itself has a fate. It might unfold slowly, so slowly we'd never feel it, or it might end abruptly in a final cosmic breath. The question of the universe's future is not merely poetic, it is a scientific one, and its answer may already be hidden in the very thing we've been exploring all along, dark energy. This force, mysterious, invisible, and omnipresent, isn't just influencing the present, it may be writing the universe's future, moment by moment, in every expanding gap between the galaxies. Let us follow the thread of time forward to imagine where this dark energy may take us. To do that, we must consider the nature of its strength. Will dark energy remain constant? Will it grow stronger? Or might it weaken or even reverse? Each possibility leads us to a vastly different ending, each more strange and haunting than the last. Let's begin with what many cosmologists currently believe is the most likely path: the Big Freeze. If dark energy continues on its current course, if it is a cosmological constant, steady and unchanging, then the universe will keep expanding. The space between galaxies will grow, then the space within galaxy clusters, and eventually, the space within galaxies themselves. At first, life will go on, stars will continue to burn, planets will orbit, civilizations may rise and fall on distant worlds we will never know, but time will take its toll. Over the next hundreds of billions of years, the stars will begin to die. The largest ones will go first, exploding into brilliant supernovae or collapsing into black holes. Then the smaller stars, like our sun, will swell and fade, leaving behind cooling remnants known as white dwarfs. Eventually, all the stars will be gone. Galaxies will dim into cold, dark husks. The universe will become a vast cemetery of failed suns and silent black holes, drifting farther and farther apart in a dark, ever-chilling expanse. Even black holes won't last forever. Over incomprehensibly long spans of time, trillions upon trillions of years, they too will evaporate through a process called Hawking radiation, vanishing into nothingness. What remains after that is silence, a universe stretched thin, colder than any winter could ever imagine, with particles so distant from one another that they may never collide again. This is not a dramatic end. It is a slow, graceful slide into entropy, the gradual loss of usable energy. The Big Freeze is not death by explosion. It is death by exhaustion. But this is only one possibility. There is another scenario, far more violent and abrupt. One that emerges if dark energy is not constant, but instead grows stronger with time. In this case, the accelerating expansion becomes more than a background effect. It becomes catastrophic. Imagine a future where the force driving galaxies apart does not remain steady, but instead increases. First, galaxies would fly apart faster than ever. Then, the stars within galaxies would drift away from each other. Next, solar systems would fall apart. Planets would spiral away from their suns. Moons would abandon their planets. Gravity itself would be overpowered, and it wouldn't stop there. Eventually, the force would grow so immense that it could overcome the very forces holding atoms together. Protons and neutrons, those solid building blocks of matter, could be torn apart. The bonds that create the fabric of reality would snap. This would be the Big Rip. A tearing of space, time, and everything within it. Unlike the Big Freeze, which unfolds over unimaginable timescales, the Big Rip would arrive suddenly, once a critical threshold is crossed. It's a universe that doesn't coast into stillness, but instead meets a final crescendo of violence. No warning, no escape, only disintegration. It is perhaps the most unsettling fate we can imagine, not just death, but unmaking. But there is still a third path. Suppose that dark energy is not constant. Suppose it fades, slowly, gently, or reverses entirely. If that were true, the universe might not expand forever. Gravity, the ancient force of attraction, would begin to take control once more. Slowly at first, then with growing speed, galaxies would stop moving apart and begin to approach one another again. The cosmic expansion would slow, stop, and then reverse. The universe would begin to contract. Galaxies would collide and merge. The sky would grow brighter with starbirth as gas clouds compressed. Over billions of years, space would shrink. The temperature of the universe would rise. Everything would be pulled together into an ever smaller volume. Stars, black holes, planets, and atoms compressed into an impossibly hot, dense state. Eventually, it would all collapse into a single point, a reversal of the Big Bang, a big crunch. And then, some theorists propose that such a collapse might trigger another Big Bang, a rebirth, a new universe with different laws, different constants, different histories, a cosmic cycle of death and renewal, a breathing cosmos. Others suggest that a big crunch would be the final end, with no rebirth to follow. Just one final moment of infinite density, followed by nothing. Each of these fates, the big freeze, the big rip, and the big crunch, depends entirely on how dark energy behaves. And that is the great unknown. We can measure dark energy's effects now, but we do not yet know its nature. Is it truly constant, as Einstein's cosmological constant suggests? Is it dynamic, as quintessence theories propose? Is it decaying, shifting, responding to some deeper force? Until we understand the true nature of dark energy, we cannot predict the ultimate fate of the cosmos, and perhaps even then, the future will remain shrouded in uncertainty. Perhaps we are only scratching the surface of deeper, stranger truths. Let's pause here and reflect. The fate of the universe is not just a scientific question, it is a deeply human one. It reveals how small we are and how briefly we exist in the context of cosmic time. It also raises questions not just about the end of everything, but about the meaning of beginnings. If the universe ends in cold silence, does that diminish the warmth of life today? If it ends in fiery collapse, does that make every sunrise more precious? Or does the unknowability of the future free us, reminding us that the story is still being written? Perhaps what matters most is not how the universe ends, but how we choose to live in it while it lasts. In our brief moment between cosmic dawn and cosmic dusk, we find ourselves not at the center of the universe, but suspended in its quiet expansion. We are made of stars, yet driven by mysteries we cannot see. Our fate is bound to a force we do not understand. And that is beautiful. It means we are part of something greater than ourselves. Not lost, but woven into the fabric of a story still unfolding. It also means that the future of the universe is not a fixed script, but a question, a mystery we are still learning to ask properly. So where do we go from here? Now that we've explored what might become of the cosmos, let us take one final turn inward. Let us consider one more mystery, one that lies not at the end of time, but in the strange and fragile moment we occupy right now. Why now? Why are we alive at the precise cosmic instant when dark energy has begun to dominate? Why not earlier, when matter ruled? Why not later, when the stars will have gone out? Why do we live at the balance point, this brief, luminous pause between order and isolation? In the final segment of our journey, we will explore this great question, perhaps the most personal of all. Let's turn now to the coincidence at the heart of our cosmic moment. Pause with me, just for a moment. Imagine the entire history of the universe stretched across a timeline, from the first flare of the Big Bang through the birth of stars and galaxies, to this very moment where you now rest, alive, breathing, aware. It's a timeline that spans over 13.8 billion years, a length of time so vast, so filled with unimaginable distances and transformations, that your very presence here becomes something rare, something unlikely, something that asks for explanation. Now consider this. In all of cosmic history, in this vast ocean of time, why do we exist now? Why are we alive at this particular moment, this sliver-thin instant in the life of the cosmos, when something extraordinarily delicate is taking place? Today, the energy from matter, everything we can touch, see, and measure, is almost exactly equal in strength to the energy from something we cannot touch, cannot see, and barely understand: dark energy. This is more than strange, it's startling. Because matter and dark energy behave very differently. Matter thins out over time. As the universe expands, the same amount of matter is spread more thinly across a larger and larger space. Galaxies move apart. Gas clouds stretch and dissipate. Stars are born, burn, and die. Dark energy, on the other hand, if it is a cosmological constant, does not fade. It remains constant per unit volume of space, and as space expands, there's simply more of it, more vacuum, more dark energy. So, rewind the clock. Billions of years ago, matter dominated. Galaxies formed, stars ignited, black holes grew. Fast forward the clock. Billions of years from now, dark energy will reign completely. Galaxies will drift so far apart, they'll become invisible to one another. The universe will grow quiet, cold, still. And yet, somehow, right now, in this exact window of time, matter and dark energy are in near perfect balance. Not too different, not off by a factor of 1,000 or 1,000,000, but almost equal. Why? This is what physicists call the cosmic coincidence problem, a strange and unsettling riddle that sits at the heart of modern cosmology. It's like walking into a room with two hourglasses. One started empty and is slowly filling. The other started full and is slowly emptying. And somehow, you've walked in at the exact moment when the sand in each is precisely halfway, balanced in opposite directions. Coincidence or clue? This question invites two very different kinds of answers, one grounded in observation, the other in speculation. The first is what we call anthropic reasoning. The logic goes like this: intelligent life, like ours, requires a very specific range of conditions in order to emerge. Galaxies must exist, stars must shine for billions of years, planets must form, cool, and stabilize. Chemistry must evolve into biology. And all of this, life, intelligence, consciousness, can only happen during a brief cosmic window. A time when the universe is old enough for complex structures to have formed, but not so old that everything has already drifted apart into isolation. In this view, we exist now because this is the only time we could exist. The reason matter and dark energy appear to be in balance is not because it's particularly special. It's because observers like us can only emerge during this narrow slice of cosmic time. The universe isn't balanced for us. We simply find ourselves in the one place, and at the one time, when the balance happens to allow our existence. It's a kind of cosmic selection effect. Just as you wouldn't be surprised to find water on Earth because you're alive and need water to survive, perhaps you shouldn't be surprised to find yourself in a universe or a moment where life is possible. But not everyone is satisfied with this answer. Some scientists and philosophers argue that anthropic reasoning doesn't really explain anything. It shifts the question, but doesn't resolve it. Why should dark energy exist at all? Why does it have the value it does? And why should that value align so perfectly with the diminishing energy of matter right now, after 13.8 billion years of evolution? These are fair questions, and they lead to another possibility. Perhaps the coincidence isn't random. Perhaps it hints at something deeper, a mechanism, a law, or a hidden structure in nature that we have not yet discovered. Perhaps dark energy isn't constant after all. Perhaps it changes in response to the energy density of matter. Perhaps it was dormant, asleep in the early universe, only awakening when the conditions were just right. Some theories, especially those involving quintessence, suggest that dark energy may be tied to a dynamical field, one that shifts over time. In such models, the emergence of dark energy's dominance isn't an accident. It's part of a process, or perhaps something more radical is at play. If we live in a multiverse, an infinite collection of universes, each with different physical laws, then maybe dark energy has many possible values. In most universes, the balance is wrong. Life never forms. Galaxies collapse too quickly or never form at all. But in this one, the numbers line up just right. Not because of design, not because of necessity, just because. This is the version in which observers can ask the question. Again, the idea is not without criticism. A multiverse can be imagined, but not easily tested. It turns science into probability. It replaces certainty with statistics. Still, whether by chance or by law, the balance we observe remains a profound mystery. To be alive at the moment when dark energy has just begun to take over the universe is to exist at a turning point in cosmic history. It is like standing on the edge of a great transition, not from night to day or from spring to summer, but from a universe filled with matter to a universe ruled by vacuum. We are witnesses to this pivot. And what does that mean for us? Nothing and everything. It means that we are brief, that the time in which stars burn, planets form, and minds awaken is short, cosmically speaking. It means that our universe is changing, and that the future may hold nothing like the present. It also means that our questions matter, because the mystery of why now is not just a mystery about time. It is a mystery about perspective, about meaning, about presence. We are not spectators in the universe. We are participants, made from stardust, shaped by forces we do not understand, capable, for a fleeting instant, of asking the very questions the universe has encoded into its unfolding. So, why now? Maybe there's no answer. Maybe the question is the point. To be here, to wonder, to marvel at the balance, to feel the awe of coincidence. And as we bring our journey to a close, let that thought remain with you, not as a puzzle to be solved, but as a stillness to sit inside, like the hush of space, like the breath between galaxies, like the silence that follows the final note of a lullaby. Let the mystery of dark energy wrap around you like a cosmic blanket, gently, silently, endlessly expanding. And as the universe drifts toward its unknown future, so too may your thoughts drift toward rest. The stars are still shining, the questions are still echoing, and sleep is waiting.